Good afternoon, everyone. I'm talking about collective assessment of active traffic management strategies using Vissim software. This presentation is based on a project assigned to NJIT University by New Jersey Department of Transportation. As introduction, I can say active traffic management is the ability to dynamically manage congestions based on prevailing and predicted traffic conditions. Due to recent development in vehicular and infrastructural communication technologies, ATM policies are calling more attention from departments of transportation. Few examples of ATM policies are provided here on the right side, including queue warning, variable speed limit, transit signal priority, active ramp metering, adaptive traffic signals, and hard shoulder running. The goal of this study is to prepare a large-scale micro-simulation network platform to be used as a reference for various ATM policies evaluation. And of course, limited evaluation of few policies are considered in this phase of our study. Our study area is shown in this slide, which includes intra-state AT, State Route 15, and State Route US 46. There are several more arterial roadways in the area, which are shown at the bottom of this slide. Finally, we came up with 34 miles of roadways, including 41 signalized intersections, most of them semi-actuated. The problem in this area is that IAT is actually close to Manhattan area, is 30 miles away from Manhattan area. So this section of IAT is experiencing lots of traffic, especially in morning peak hour and evening peak hour, because people are commuting from New Jersey to Manhattan in the morning and evening for actually working purposes. The available field data for this study was very limited. We only had volume count on 35 sections, which we normally used for traffic assignment. We also have the travel time data on IAT, US 46, and US 15, which we used for calibrating our model. Okay, so to assign the model to assign the traffic to the model, we decided to deploy dynamic traffic assignment. But the problem was that we had no OD matrix, but we decided to just start from some rough assumptions. So we defined 18 zones in our network based on physical characteristic of the roadways. Basically, adjacent intersections were considered to be in the same zones. To make it more realistic, we adjusted relative flow at different entrance for each zone based on adjacent intersection control type and number of lanes at the entrance section. So in conclusion, if we had several entrances for a single zone, each zone would actually have a flow based on relative to the number of lanes at that section and the immediate intersection control type. For dynamic traffic assignment, as a start point for dynamic traffic assignment, we assumed a seed matrix of 9,000 trips per hour, which was very rough assumption. And we assigned this seed matrix to the network. Our goal was to assign this matrix to the network and apply the matrix correction based on the volume we had on the links, and then compare the result to see how close we are to the real world volumes. Applying the seed matrix to the network after 15 iterations, of course with constant random seed, travel time was converged on 90% of paths with tolerance of 50%. For matrix correction, we actually had to run simulations several times for different hours in peak time. Our goal at this stage was 3 hours. So the advantage of Vissim software is that the matrix correction module is available in this software, because matrix correction is more on macro simulation softwares, macro simulation studies side. So this module is available in Vissim, and we used it. We updated that seed matrix, and finally we came up with several matrices with range of 1700 to 1900 trip per hour. So the next step was to assign the updated matrix to the network. But this matrix was very big, and it was not possible to assign it to the network with actually single iteration, the whole matrix. So we used a reduction factor of 40% and increment rate of 1%. These values were achieved based on several trial and error and fine tunings. And after 60 iterations, the convergence was achieved for 90% of paths with a tolerance of 15%. As we started with a very rough and unrealistic seed matrix, we need to know how compatible our model is with real-world circumstances. So we compared the ground truth volumes on the links with the volumes coming from our model. It doesn't look perfect, but it's not bad, because as you can see, in most sections, the volumes are compatible. In some sections, of course, not. So to make it more realistic, we decided to calibrate our model based on travel time from the field data. We converted dynamic paths to static routes, because our goal was to adjust the volumes and weaving movements to make our travel time in different sections more and more compatible with the travel time coming from the field. So in this slide, you can see travel time comparison between our calibrated model, which is the blue color, and the data coming from the field. So on the left side, you can see the comparison for a section which in a peak direction, of course, which is pretty fluctuative, and calibration was time consuming. On the right side, you can see that for another section which is in off peak direction, the travel time is smooth and not fluctuative, and the calibration was more straightforward. We did it for several sections on IAT, US 46 and US 15. The next step for us was to evaluate the impact of some ATM policies deployment on the network. At this phase, we selected hard shoulder running and variable speed limits. There are several models developed for active traffic management policies, but when you want to deploy a model in real world, the model needs to be simple. Unlike the models developed in academia, real world models are simple. So we tried to find the models which are already in service in real world. So for hard shoulder running, we use French A4 A86 motorway algorithm, which is used for hard shoulder running. This roadway has the same speed limit as IAT. And the criteria for triggering the hard shoulder is based on occupancy of the section. If occupancy is greater than 20%, the hard shoulder opens. If it is less than 20%, the hard shoulder closes. For variable speed limit, we use multi-level coordination search algorithm, which is in use in Sweden. So in this algorithm, the triggering criteria is based on speed. If a speed is less than 45 km/h, the variable speed limit signs start functioning and reduce the speed from 120 km/h to 60 km/h. Actually, the variable speed limits needs to be placed in 3 sections upstream, because that's a big reduction in the speed. Here you can see our physical configuration of the network for variable speed limit and hard shoulder deployment. On the left side, for variable speed limits, we placed the speed data collection on the section which we observe the congestions, and we also put the variable speed limit signs on the upstream. And using COM interface, we actually run the model for 3 hours in PM peak, in evening peak time, and we also collected the travel time data, and we compared the travel time between base condition and when the VSL works. It doesn't show, it shows some, the variable speed limit shows some little improvement, I can say. And on the right side, you can see network configuration for hard shoulder running. For hard shoulder, we need to collect, based on our model, we needed to collect occupancy on our critical section. And then if occupancy is higher than that threshold, the hard shoulder opens. Here, we selected a longer section for travel time comparison, because when you run hard shoulder, you really need to know what happens at the downstream, because you are releasing more flow to the downstream. So, and at the bottom in the right side, you can see the comparison between base condition and hard shoulder running deployment. It seems hard shoulder is making the situation worse, because you see more fluctuation, and the overall travel time seems to be increased. And based on our visual observation, it causes congestion on the downstream when hard shoulder starts running. As a fresh scenario, we decided to deploy both hard shoulder and variable speed limit in this section. So the occupancy data collectors are working here, and the hard shoulder opens in case occupancy is high. We also located a speed data collectors on the downstream. So if a speed is dropping in the downstream, the variable speed limit signs located at the upstream of our hard shoulder start working, and basically they kind of control the volume going to downstream. And as you can see on the right side, it noticeably improves the travel time. I mean, it reduces the travel time. So, and what we found from this stage of our work was that deployment of combined ATM policies could be noticeably effective in some cases and should be considered prior to extensive deployment of ATM policies at the network. And our next step of this study for us is to have a widespread deployment of ATM policies on IAT and evaluate its impact on the whole network and on adjacent roadways, especially US roadways, which are US 46 and US 15. I would like to say thank you everyone for your attention, and also a special thanks to PTV Group, which gave me a chance to present my work.